I typically remind here a nice quote by Richard Feynman. You know Feynman? Never heard. The most important physicist of last century. Nobel Prize. When you ask a physicist, name 5 important physicists, they say Einstein, Feynman, and someone else. And Feynman used to say that physics is like sex. It can have some useful outcomes, but this is not what we do. Okay? We study a number of different things. We can explain why Cosimo de' Medici took power in Florence, even if it had a small family with a few members instead. Or why, you know, a new product, you've seen something with Miriam, and the social side. It's an important side. And whatever you do, you can generate new insights when you study these things. But there is a more important thing on why we study networks. And the important thing is because network is a representation of a system, can be. And we live in a world which has a high level of complexity. And this complexity, which can be expressed by saying that we have many elements, we have relationships that are not always that simple or linear. You see sudden transitions, net systems self-organize, and so on. I mean, there are a number of... But the most important thing is that behind any complex system, there is a network. There is a certain number of elements. There are connections between these elements. And these connections, these interactions, are the most important side. And you cannot understand the system if you don't understand the network that is behind the system. We have several types of systems. Some may be very simple. Some may be very complicated because they have an incredible number of parts, but still put together in a simple way. If you get a car, for example, or an airplane, you have millions of parts, but there is only one way to get those parts and build a car or an airplane instead of 3 guns and two chariots. Or maybe systems that even if they don't have many elements, their behavior is most of the time not simply predictable. I don't say unpredictable as many say, because this is not completely true. But it's not simply predictable. And the most important thing is you cannot split that system into pieces to understand it. One of the things you've always been taught is that if you have a complex problem, what do? You divide it into simpler problems. This doesn't work with a complex system. You cannot divide it. You cannot do. Because if you do, you have a partial solution that may affect the rest of the system and you don't know how. And if you try to look for simple solutions to complex problems, you may run into trouble. One of the best examples I know is what happened with the codfish ecosystem in Canada a few years ago. Now, for an incredibly extensive use of fishing, codfish, which was the main resource of a certain area in Canada, were starting to decrease. Okay? They end up with a very few species left. And so they tried to find what was the problem. And the problem was identified with an enemy. When you have a problem and you know how to solve, you look for an enemy. Okay? Because if you fight the enemy, then you think you solved the problem. So the enemy was identified as a seal. The seal typically eat fish and eat a lot of codfish. So they say, if we destroy or reduce the population of seals, we may increase the population of codfish. If you remember some years ago, what happened with the seals in Canada. So they tried to do, and the result was, yes, seals eat codfish, but eat also many other fishes that are natural enemies of the codfish. So if you destroy seals, those population increase and the codfish decreases. And so they ended up with no codfish at all. It's almost extincted in Canada. So this is one of the examples in which if you try to find a simple solution to a complex problem, you may run into trouble. By the way, many times the same system can go through different phases. Can start as a simple thing and then may get complicated. If you want to have a wonderful example, you go home, open your faucet. If you open a little, you find a laminar flow of water. If you give some more, you start to see a turbulent, and then if you open everything, you have a chaotic behavior of your water. And it's always the same system. If you modify a little certain parameters, the flow of water, you totally change the behavior. Okay? So, the idea is, we find networks practically everywhere. They typically describe how the different elements interact. And if you know how to describe those interactions, you may reveal patterns that you couldn't see in different ways. One important thing is that the structure of the network has a big impact on the functions. And this happens on many occasions. The structure of something has a lot to do with the function of that system. If you change the structure, you change the functions. And today, we have technology available, so this helps a lot in trying to understand how a network works. Now, the problem is, how do we study networks? First of all, it is an abstraction. Okay, we identify elements and we say these are the nodes of the network. People, companies, objects, neurons, chemical elements, whatever you want. Then you try to identify what are the connections and to define the connections, maybe friendship for people, maybe economic relationship for companies, maybe chemical reactions within different elements, maybe connection between neurons and so on. And you can draw a little picture. This picture may be complicated by a number of different parameters that take into account different situations. You may have a weight on the relationship. That is, all the relationships are not the same. Some are stronger, some are weaker, some may mean more. If you have, for example, a network within places, the weight can be the time to go from one place to another. That is depending on a number of different parameters and so on. Network may be directed. I mean, I can have a link with something else, but the vice versa is not working. typically a website. A website can have a link to another website, but not always the second website has a link to the first one. You can assign values to the different elements. You may have large companies, small companies. You may have faster reactions, slower reactions, and so on. You can have different layers. You can have a certain dynamic behavior during a certain period of time. Network can grow, can become smaller, and so on. All of these aspects can be studied, and all of these aspects will give you some ideas on the different behavior. Yes, but how do we do? We get the network at the end with this abstraction, okay? So we can play with pictures. Funny, but not too much. Or we can build a little scheme in which we identify the different elements and we put a number there whether there is a link. Can be a single number if it's a link, can be a real number if there is a weight, can be whatever. 0 means no link. 0 means that from V1 to V2 there is no direct link. Okay, 1 means from V1 to V3 there is a link, and so on. And now what's that? What is this one? This is a matrix. And we have matrix algebra, which is a very powerful tool. And with the tools of matrix algebra or linear algebra, you can do whatever you want with the network. And you can measure a number of different aspects, and you can understand a number of different things if you're using algebra. I know you don't like mathematics, but this is the way we play. We also have software tools that do these things. Because being algebra, what is an algebra? What do we have when we have a branch of mathematics dealing with something? You have a number of formulas, yes. And you have a clear way to go from one formula to another. Okay, so you can put that one into a piece of software and let the software do the calculation. You only need to understand what you're doing. That's the little thing. And the understanding of what you're doing is very important. Because here you're mixing up a number of different areas together, whatever. You're really working by analogy. What does it mean, working by analogy? What is analogy? It is, I have an area, I have a second area. If I can find the link between them, then something in one area may be similar to something in the other area. This is the best example of analogy you know. The simplest. The simplest is this one was the one writing. What is the simplest example of analogy you know? The one you're using the most? What is this? Here we're giving a rule to go from algebra to geometry. Okay? And what is the advantage of this analogy? The advantage is that if I have a function, no matter how complicated, and I don't know how to solve it algebraically, I can draw it and find the solution here. And these are exactly what I need. So I move my problem from an area I don't know how to deal with to an area I know better, or it's simpler, and I solve my problem. I can do the opposite. If I'm better at algebra than at geometry, I can derive the formula of this one and solve the formula. Okay? What you do when you do a regression analysis. What is a linear regression? A linear regression is something from which I get a number of observations, no matter how spread. I try to find some way a relationship that I can express as something like A x plus B. Okay? You remember? Seen it? How do you do that? You have a piece of software that does it. When we didn't have a piece of software, not many years ago, glaciations were already ended and dinosaurs were already extincted. We did things by hand. Now, the formula to arrive to this one, it's a bit complicated. But if you draw well on a piece of paper, and you have a good eye, and you can try, you can draw a line there, and then you can measure. You measure this angle, you measure this distance, and you got it. And it's exactly valid as if you had done the calculation. Try if you don't trust me. You need a bit of exercise, but if you were forced to do calculation, I can tell you, you do a lot of exercise in finding the right line there. We put a number of things together to solve our problem. We, anyway, must be careful. This is a wonderful paper. Not very easy to read, as you may imagine, but it's a wonderful paper. And the best thing of this paper is the first sentence. So putting things together doesn't mean putting everything in a basket and see what happens. Okay? You need to do it with caution, otherwise your stomach may revolt. And I tell you, I've seen many examples. What we do so is we model. You've seen a model before, a model for a process. You can model a system. What is a model? In general, a model, what is a model?
It's a possible solution done by an example way of acting.
No, it's not a solution.
Some kind of prediction. Some kind of prediction. I don't know, simplification. application of some things that
To make a model, to create some situation.
Then I use the model to make a prediction to understand it. But what is a model per se?
I mean, structure. Just a visual representation.
Not necessarily visual. It's a representation. It's a representation, a synthetic representation, the simplest representation I can for reaching a specific objective. If I need to walk in a city, I need a map, which is a model. If I am in the subway, I need a subway map, which is not the map of the city, it's different. Okay, it doesn't give me all of the details of the streets and so on because I don't need them. And that's another model I can use. Okay? And when I use this model, I need to play in a certain way. I need to acquire a certain, what I call a mental machinery. That allows me to work with the model, which is different than working with an example, data, and so on. Because here I'm losing a number of details because they are not really needed. But losing those details, I may gain in simplicity, and so try to understand better what's going on. And one of the tools we use, mental tool, is analogy, as we've seen. If I can find the link between two areas and I can solve something in an area, I can find the solution in the other one, okay? If I establish a good link. The second, and this can be, is the same also not only for systems or for example like this one, it's also for processes. For example, there is a branch of physics that study fluids, and there is a well-known series of explanations on how a fluid passes through a medium. It's called percolation, which is quite important, mainly for an Italian, because it's the same phenomenon that gives you coffee. Passing a fluid through a medium. And you know exactly, for example, what type of density can give you, what type of fluid and the output and so on. You have all of these things are being studied for years, centuries. And then you make a link and say, well, if instead of passing a fluid through a medium, I pass a message through people, is it the same process? It's exactly the same. Okay? So I can use exactly the same results to understand how a message may spread in a group of people. And so I can use it for marketing, for example, because I know what type of characteristics my message needs to have and my group of people needs to have in order to achieve some objective. I can study how a virus spread in a population. And this is where epidemiology was born. Because the phenomenon is exactly the same. I'm infected. If I'm close to someone else, I can infect it, and so on. I can study how a fire spread in a forest, and so on. All using the same explanation. And the last thing is, mainly with network, we're studying their shape from a topological point of view. Now, you know what topology is. Topology is the study of how I can modify an object without changing the basic properties. So, for example, if I get this one, I get this one, and I get this one, these are the same object. Okay, because I can modify this one into this one into this one without structurally changing my object. you think made of rubber. But this one is a different object, because I cannot go from this one to this one without cutting. Okay. So studying the topology tells me a lot about the real structure of something, even if the shape may look different. Okay? If I want to study shapes, I use geometry. If I want to study structures, I use topology. And here the way of doing things is a bit different. Because, for example, I don't care of the physical image of a network. Because they might be given by geometric considerations. But I need to go a bit deeper to understand what the real structure is. But the most important thing is, all of you have been told that there are different ways to approach a problem. To study it quantitatively or qualitatively. Okay? All of you have seen some type of research meet or something like that. Okay? Here, this doesn't work. There is a famous sentence by Deming that says, without data, you're just another person with an opinion. You know it? Well, this is a typical example in which the opposite as well works. And this, without an opinion, you're just another one with data. You cannot split. You cannot change things. You need to use both views. Because one of the two risks giving you wrong or a misrepresentation of what you are studying. So you definitely need to measure and then to understand what you've measured. Okay? To give a context for those measurements. Otherwise, you don't know what you've just played with numbers, which is maybe fun, but. So we use the mathematical property to measure these things. We use a number of different models there. If you are worried that there is a strong, rigorous framework in which all of these objects has been put, and the framework of what in physics is called statistical physics or statistical mechanics, which is a very rigorous framework that allows you to do all of the things we are doing. We need to understand what we're doing. If you don't know the system, you'll never understand anything about the system. The nice thing is that since we're playing with numbers, then we can run simulations. We can modify, we can change, and see what may be the different possibilities, and so on. We have a number of things we measure. What you lost? You have lost what?
No, don't worry.
And we can measure things typically at three levels. You have a global series of metrics that give you the global view, general view of your system, from which you can understand a number of things about the behavior, possible reactions to external inputs, and so on. You can say a number of things about the intermediate structure of your network, which is important. They're not always looking the same. Or about the individual elements. For example, assigning importance to the different elements or trying to understand what is their role in certain processes and so on. Again, You need to read those things. Here there is a number of definitions that allow you to measure. For example, one important element is the density of connections. There is a maximum possible number if you have a certain number of elements. That is, everyone is connected to everyone else. When you measure a network, you see that the density is important because it's gives you a first idea of how connected is that system, on how not connected is the system. Then, for each element, you can count how many links it has to its neighbors, and so measure the distribution of those links. And that distribution, the form of that distribution, tells you a lot about the type of system you're dealing with. And so on. You can measure, for example, the distance between any two elements. And this is important because, for example, one element which is closer than the others to any other may have a different role in your network. You may measure the efficiency of that system with respect, for example, to the spread of a message or an opinion or whatever. And so on. We'll have a look later on. Now, I know you get scared when you see a formula on a slide, so I put all of them in a single slide, so you're scared only for one.
Oh, this is better than my list to go to see this chapter.
Yeah. No, maybe it's clear. It's just a different language, but you don't speak that one. But it's not a problem because we have a wide range of tools that do those things. So what you're called to is to understand what you're doing, to understand what's coming out. Calculations are done by software. Today it's easy. Some time ago you would have done by hand. That's why our sociologist friends have spent 40 years with a network of 5 people, because if you have 200, I tell you, it's a nightmare. Okay. We'll be using this one then. I'll show you a quick thing this morning, and then this afternoon you'll play with. Because it's... Did you install it? Tried? Open and try? Who didn't? Who did? The others? No.
Just managed to download it. So. Oh yeah, that's it.
You're lacking of an important quality that will let you survive in this world from now on. And this is called curiosity. If you are not pathologically curious, you are dead. Pathologically curious means that if I get into my room at the hotel, I cannot resist opening all the things that can be opened. I cannot stay with my hand in my pockets. If you put me in a room with that one, I need to open it to see what's inside. That's my... Anyway, there are several things you do with the network. One is obviously showing the network. And this is a nice exercise because, as you'll see, this is meaningful if you have a small network. This one is clear. If you have a network of, let's say, 100 nodes, you end up with something like that. This is totally useless. Every time I run the paper with the network, some reviewer asks for the picture and say, well, I give you. What do you do with the picture?
Yes.
Hmm?
The people that like art.
And they like art. But it's difficult because, for example, if you have this one, unless you measure you don't see that this network has this structure. You cannot see. Or you cannot see that this one is something like that instead of looking like a network. If you don't measure, you will never be able to understand that that is not a system. It's a collection of pieces. Or that this one is a strange type of system in which some elements are two groups and the links are only between groups instead of within a single group. You don't see them unless you measure something. Or what's the difference between this one and this one? Can you see it? Is there any difference? Only if you've seen thousands, you may have a hint, but you cannot be sure. But when you measure, you can see that, for example, the distribution of the link of this one has this shape, and the distribution of links of this one has this shape, and these are totally different. That means a totally different behavior, a totally different configuration, and so on. So you need to play with numbers a bit. I was telling you, you have a number of results that are totally unexpected if you look only at the qualitative side or something like that. For example, I may imagine that if I grow a network, the average distance between nodes will increase. It doesn't work that way. I would expect that one, and this is what I find, which is a totally different story. Why? I don't know. Or you may think that if I start cutting connections, after a while, I destroy my network. Okay, this is true. The problem is when. Is there a limit? And you find out that there is a limit, but it depends on the network. For example, if you have a random distribution, roughly, a normal distribution of links, you have a critical fraction after which your network is destroyed. You have a number of pieces, as you've seen. But if you have a distribution like the one we saw, a scale-free, that is an exponential or a power law distribution with a long tail, then, well, it depends on what you're removing. Because if you're removing randomly, you practically don't destroy the network until you have removed all of them. You still have ways to go from one side to another. But if you target the most connected nodes, then with 3 or 4, you may destroy the network. Okay, now, knowing what is the distribution of the connections can help you understanding what are the characteristics of robustness of that network, and what you can do to increase it or to decrease it. I want to increase if I want to tighten the network. I want to decrease, for example, if the process I'm studying is the spread of a virus. I want to destroy the network. Because if I can stop the spread, and here, for example, we know that for an epidemic infection, traditionally, we know that there is a critical threshold. That is, if the density is not up to a certain level, we don't have any spread of infection. But it depends on what are the relationships. Okay? Or, we typically think of a tourist destination as an assembly of different groups. And we all, not me. You all study a destination knowing there is the group of hoteliers, the group of restaurants, and so on, okay? And when you have a plan on when you build up a policy or when you do something like that, your destination manager will be talking to the representative of the hotel association okay, and so on. Wrong. Because the real structure is not that one. The real structure is a mixed structure. You have groups, but they are formed by different type of businesses and so on. And when you understand this, you understand why, for example, in many cases, certain policies don't work. Because here you cannot think you're working with the system. You're working with individuals. This is a group of hotels. Are hotels connected between them? No, they fight each other. Okay, so this is not a system. Any policy you do for this thinking it's a system may only fail. This is one of the reasons why I say that today the industrial associations are the worst thing you may have in a destination. I can show them. If you had no association, you would live much better, but that's wrong. One more thing, if you are in a company, who's the most important person in the company? The CEO? Oh, it depends. Because if you draw the real network of communication, this is a wonderful study of some years ago, then you find that the most important element is this one, okay? You agree? And this one is this, not the CEO. Conclusion, in a company you can remove the CEO, not they work well. But if you remove that man, you may destroy the company. Okay? Now this is important because it's a completely different view from the traditional view, and they give you a different perspective. We were talking about topology. Stupid example. These are 6 different configurations. If I measure geometry, the distances, I obtain these that are obviously totally different. Okay. But if I define distance as the number of links you have to cross to go to a different node, then all of them have exactly the same distribution. And this is what gives me the main characteristics of these configurations. I may need the geometrical view in certain situations, but typically I'll be working with this. So all of them are the same. By the way, they will have same characteristics, no matter whether this is a tourist destination, this is a neural system, and this is I don't know, a street network. They have topologically the same characteristics, so their behavior with respect to certain dynamic processes will be the same. Okay? Which is a totally different view of what you typically see. Main models. You can have a random distribution of connections. That's the typical simple model. Here, basic statistics apply. What you've been using so far. Or you can have a situation in which some of those parameters are different from a pure random distribution. For example, you have a clustering which is a local density which is higher than expected, and the length of the path which is smaller than expected. Or you can have a distribution which has a long tail. This is like an exponential of a power law. This is what typically happens on the web. Think of how websites are connected. You have a very few websites with billions of connections, and then a lot of websites with very few connections. And this distribution helps me understanding what type of dynamical characteristics the system may have. For example, here it's relative. There will be my threshold for destroying the network. That is, there will be a threshold for spreading a message. If I don't start spreading the message from a certain number of elements, the message will not spread. While here I can start with a very small number of infective elements, provided I choose them well. If I start from those with high number of connections, then my spread goes much faster, and so on. This is just an example of the many things you can do. You can obviously measure. You can have a number of measures. You can use Gini index. You can whatever it is. I mean, don't know what you know. How is your statistics? What? Okay, anyway, there are ways to measure these things. Sometimes it's a bit delicate for those who remember some statistics. You cannot really use standard tools because you end up with strange results. You need to do special algorithms to find, because you have a number of elements for the standard way of fitting this curve that may disturb you, but forget. One of the things you can do is to study the internal structure. And so, for example, to find whether there are communities. Community is a group of elements that are more connected between themselves than with the others. You don't see them, we've seen before, so you need a special procedure that will run and will give you a statistical view of those potentials. And then you check whether that has a meaning in your context or not. May have it, may not. It depends on what you find. Or you can look for a hierarchical structure, okay, which is typical of certain systems, and you can measure. Now, when I know what is the internal structure, then I start understanding a bit better what is the internal behavior of my system. I can have something with totally no structure. I can have a structure on a single scale because there are I can identify a number of different groups. Then I will go and see how those groups are built and so on. Or I can have a hierarchical structure that is a multi-scale structure. I have big modules, and all those are still divided into other modules and so on. Some of these are typical of some of situations. So this is a stupid example. It's small so we can see. And we can see also without measuring. Then I'll show you how to measure. But you see that this one is out. So no matter what the system does, that one is totally forget it. We see that there are a few groups, but this group is disconnected. So for example, if you want to spread something from here, you will never reach this one, no matter what you do, or this one. There are special elements. This one is very highly connected. There's a number of connections. This one is a bridge. If I remove this one, I cut this connection. So that's an important element, but it's also a bottleneck. Hmm? So depending on what I'm interested in, this is a very important or a very delicate element of the network. Okay, just like this. If instead of removing this one, I cut this connection, same story. Okay. I have a number of measurements I can do. I'll show you how. Those numbers will tell you nothing unless you compare with other situations. But if you are inside this one, you can see, for example, if I want to identify the most important element, well, the first thing I will ask you is define what you mean by important. What do you mean by important? Who's the most important? The one who has most connections is one way of defining importance. Or you can say the one who can more easily reach all the others. That's another way to mean important. That may be different. And you see that these are different. Some may be the same, some are different. Or important may be those that are the bridges, or those whose neighborhood is very connected. I'm important because my friends are very connected between themselves. And these are different views, and it's difficult to understand what is the most important element unless you define it. So you need to define, and so you can measure. And you cannot just say that this is the most important because it has the highest number of connections, because here is not the most important, here is not the most important. Qualitatively, you would have identified one of those. But then if you measure with respect to certain processes, you may change your mind. It depends on what you mean by important and what is the phenomenon you're studying. You can also combine them if you want a single measure. You get all of these and you put them together. For example, a geometric mean. And so you may identify a general importance of your node. But still, it depends very much on the context. It depends on what you're doing, what you're studying, what is the phenomenon. In this world, the data collection is a tricky point, as always. What is data collection? 98% of the time and the effort you do in any type of study. Because the rest is stupid piece of software that does a calculation in 3 minutes. You spend months collecting data. And here you must be careful. You must be careful because there are a number of issues that may really spoil your results. A few suggestions. First, here you cannot sample. Sampling works in a normal world. And in the vast majority of networks you study, there is nothing normal. All distributions have long tails. So you cannot sample because you don't know what you're sampling. Sampling means that if I get a decent number of random elements from here, I reconstruct that distribution. Okay? You remember? Someone told you. If I get a random number of elements, will never be able to reconstruct this distribution. Because it depends on where I'm sampling. If you have a relatively normal word, you can sample and still recognize. Okay? But here, if you miss that one, you have a totally different situation. Okay? So just the random sampling is typically totally useless. So you need to collect as much as possible. Then there are methods to understand how good is your collection of data and so on. It depends on, again, what you're studying. If you're studying companies, for example, today, a good representation is the series of their websites. Because websites are easy to measure. You see whether there is a link between a website and another one, okay? Is there? If I have a company, do I put a link to another on my website? Do I put a link to another company when? When I have some relationship. Not with the competitor, and so on. So if you get a picture from the websites, you can have a reasonable representation of what the real series of connection is. And so this may speed up the work a lot, because you're looking at websites instead of going out, asking, getting documents, and so on. Some networks are non-trivial. If you, for example, this is a network in which the shortest path between C and B is this one, length 1. But if I put a weight, the shortest means the lowest weight. And so between C and B, the shortest is this one. And this is a different story. Okay? Or if links have directions, the shortest between C and B is again going through here, because I cannot go directly from here. Here there is a link only in one direction. So I must be careful to define well your network. And if you have weights, for example, it depends on what you're looking for. Now, one of the problems is that I find, in general, is that since not all the software used for network analysis are able to handle this type of networks, people try to simplify. Because they don't know how to use the software. Tourism scholars typically don't get well along with software tools. They are very good at pushing buttons. But if they have to write a few lines of code in a stupid language, they don't do. Now, the only possibility to you to take into account all of the features is you write your program. There are wonderful libraries in wonderful languages, may be easy to use. If you know Python, for example, it's a very easy language to learn. Wonderful libraries that can give you all the flexibility you want. But if you want to use a piece of software, like Gephi, for example, we'll see, or very much used in UCINet because it comes from the sociological tradition or something like that, then they have limitations because they've been built for different purposes. So you don't have that one, and what you do, you try to simplify. No? One simplification is this one, for example. If I have a weighted network, I put a threshold and say there is a link if the weight is higher than. Reasonable? You find hundreds of papers written. Totally stupid. So this is the full network of London roads weighted by traffic. You find the data online. Not easy to build a network, but you find them. Now, if I can do have a cutoff at, let's say, the highest 75% or 50% or 25%, but I put a threshold. And I say there is a connection if the traffic is higher than. Otherwise, there is no connection. But you see already here that there is a difference. And you see here that if you rank, for example, the different nodes that are the different intersections, you have a different story, depending on what have you cut and so on. So you end up with the result that doesn't tell you a good story. It tells you a partial story. And may be misleading if you are trying to use this to do something. Since I wanted to show you at least a little of that stupid tool, so that this afternoon you can play a little and see what happens, I give you only a small hint of what we've done in tourism, but if you are really interested, you know where I am online. You go to Scholar. You know Scholar? Who's not using Scholar?
Nobody. If you ask like this, nobody will raise their hand. I can tell you. There is a little bias.
Go to Google Scholar, put in my name, and you find all my papers. Miriam as well. I am one of the few that typically puts online everything.
Me no.
I don't care about copyrights, and I put online everything I do, or almost everything I do. Sometimes just because I forget. So you find practically everything I've done in this field. Because my idea is I do research for the others, not for myself. So, summarizing, obviously, this is a wonderful area for network studies because we're living on connections of many kinds. And what we've done is we've understood something about structural characteristics of a series of destinations, for example, something I've shown you before. You've measured, because you can use some of those to measure what are the attitudes, what is, for example, to collaboration. So that then you can check with the typical survey in which everyone collaborates, but this doesn't match with what are the real connections, for example, or things like that. You can discover, as we've seen, the different type of communities and how they are built, and what type of actors play in those communities. And this is important if you try. Well, we have also run a series of simulations to see how modifying networks can change certain type of processes, how to optimize, for example, the diffusion of knowledge, information, or how to make a network more efficient or less efficient if you want to change and so on. We have complex systems to deal with. One of the possible, is not the only one, it cannot be used alone. Representation is the network representation. We have the methods, techniques, even much more than you need. There is an incredible number of suggestions on how to measure things and new measurements and so on. It's nice. From a theoretical point of view, it's wonderful. And sometimes you also find some practical things. Now, how much time we have before lunch? 15 minutes. So I'll quickly show you a few things. Then the idea is, we'll see a bit better this afternoon. Then I'll give you a couple of examples you can play with. We can discuss. And those will be two real examples. Because at the end of the discussion tomorrow, I'll upload the two papers that discuss those two examples. So you see some of our conclusions that may be different from the others, because I mean the interpretation is always okay. One. Let's go. Well, that's all. It's a bit strong, but okay. Now, if you have installed Gephi, this is the network we saw in the slide. It's one of the sample I gave you. I think it's the first one. It's a nice tool. As I say, it's something in between a real tool and a toy. Obviously, there are some simplification, but there are also some sophisticated things. So can be useful for, let's say, basic things. You have basically three panels. One is this one that's where you'll be working, okay? The second one is called the data laboratory, and practically has a table. It's a table where all the measurements will be put. So you have the numbers, not only the picture. And you can download them as a standard CSV file, an Excel file, or whatever. And then you have a preview that is basically just a static picture representation. If you are in love with good pictures, you can play here, changing colors, and totally useless. But here you have two important things. Here you can work on nodes and here on edges, and you can basically define color, size, and something like that. And this can be useful because, for example, whenever I make a measurement, I can color the nodes according to the different measurements, so I can better see something. Same for the edges. For example, this is not weighted, but if it's weighted, I can show different colors, different sizes, and so on. Obviously, here I can get any element I want. I can move it to have a better representation. Down here, you have a number of possibilities to define edges, labels, and so on. One thing I typically do, for example, this highlight selection means that when I go to one, I smooth all the others and I can see the immediate network of that one. It can be useful sometimes to explore things and so on. I mean, you can, as usual, there are hundreds of possibilities. I'll show you three and then you can play. Here you have these statistics, and here you can run all of the measurements we wanted. For example, I can say give me the average degree. That means it will calculate all of the degrees of my network. So here I can see the distribution. They invest a lot on the graphic side on this side, and here these lousy little dots. Fortunately, then, I can close this one. Then if I go to the later laboratory and I see nodes, you have the numbers. So typically, I forget those things. Or you can have, for example, the density. Okay, if you run the density, undirected, you can choose. Density is 0.092. Now density is the ratio between the number of the links that are there to the maximum possible, so 0.009 is very low. You can measure, for example, you can highlight the connected components. Now here I see what are the connected components. It tells me that there are 3. Here it's easy because I see them, but on a network with 100 nodes I wouldn't see them. So I wouldn't know whether there is a single component or there are different elements. Now, now that I have calculated my connected components, for example, I can get the nodes and say, well, look, the color, instead of being the same, choose the component ID and apply the color so I can see my 3 components. I can color my network in different ways. Sometimes it's useful. What else? You can have, for example, the average path length. Or network diameter gives me a number of different measurements. Betweenness is the one that measures how important is your role as a bottleneck or as a bridge. Okay. Closeness is how close you are to all the others and so on. Say okay, and you can have the distributions here, but what's more important, you have all the measurements here. Okay, so you can download the measurements and then do another series of calculations. Get a better picture of the distributions, or use them to do other things. For example, if I get another network that I'll show you this afternoon, this one, don't remember. Come on. Don't save. I don't remember whether this one was. Okay, this one is a bit more complicated. For example, here in the statistics, I can say modularity. Modularity runs one of those algorithms to find the different communities. And will give me a number, which is a modularity index, that is normalized, so it goes from 0 to 1, and say how good is the split into different communities. If it's 1, means I have a number of totally disconnected communities. If it's close to 0 means I cannot find communities. Yes, I find, but they are practically non-existent. Huh? So 0, 4, 0, 5 means there is a relatively reasonable series of communities. For example, I can color my node by modularity class. And so I see how my different communities were identified. I can also do other things. For example, I can filter. Say I want to see attributes. Where is it? Partition. Say I want to filter by modularity. And I want to see what is only the community, don't know, community number 6. I see only community number 6. Say now I want to, don't know, I had calculated before, no I didn't, so I don't have it. Let's say I calculate the average degree and say I want to color instead of by modularity by degree. And so you can play for years until you find something that surprises you. Okay? For example, this one has, if you look at the nodes table, apart from the ID, there's also a type of business. This comes from a destination, so it's an association, bed and breakfast, an hotel, a restaurant, or something like that. I mean, defined in a certain way. So, for example, I can see I have this filter, and I can color my community, instead of by degree, by type of business. And you see that my community has been built out of a series of different objects. You see? If that division by business were that important or that real, I would have had a majority of nodes with the same color. You agree? Yes or no? So I would have a community mostly hotel plus someone else. Community mostly association plus doesn't happen here. Maybe some of the communities. Let's remove the filter. We had identified all of the communities. Let's apply to all of them. You see that there is no area. You remember where were the communities? I can show you the modularity class. So these are the communities. So you remember vaguely where they are. If I measure now by type of business, you see that there is no area in which there is a majority of single colors, probably this one. You read them this way. You don't, but I tell you. Okay? Oh, by the way, here you have the layout. There are several types of layout you can play with. For example, this one is called Force Atlas. You say, and you have a different type of representation depending of the different layouts. You typically play a little until you find something that satisfies you as a layout. Okay? Then you can adjust a bit. These are all built thinking to have springs between the different nodes and settle a system. If you put springs in a complicated environment like that, the system tries to settle in the lowest energy configuration. And so you move pieces here and there until you find a kind of optimization of the distances and so on. This is about now. All of the layouts are nice and interesting if you have a network like this one. Those are nodes and doing something like that. If you have 200, who cares? I mean, you see a cloud there, so it's difficult to understand. But if you want to see a bit better, you have, for example, this no overlap that says don't put nodes one over the other, so you can better see them. And if you want from here, you can have also the labels. Now, if you say, show me the label on the nodes, you typically have a mess. But you may want to say hide non-selected, so that you have a label only if you select a specific node, which may be interesting or useful if you have assigned labels. Labels are these, the names of the nodes. If you assign them with a certain criteria, it may be useful to identify visually who the elements are otherwise. Questions?